All right. Well, thanks everyone for coming today. And we have a special treat again today. Thian Yew Gan is visiting us, has been visiting us from the University of Alberta in Edmonton. Thian is here as a series visiting fellow, as a sabbatical. And we've been working together since he's been here on some permafrost issues. Now, Thian has quite the background. He's been there in Edmonton since 1993. He's a research ambassador of German Academic Exchange Service, fellow of the American Society of Civil Engineers, and lead and contributing authors of the AR6 Working Group 1 of the IPCC. So he's done a whole lot, lots and lots of research, he's graduated something like 18 PhDs through his career, 30 master's students, put me completely to shame. Very interesting also is that he co-authored a book with Roger Berry called The Global Cryosphere Past, Present, and Future. And Roger, of course, was the former director of NSIDC before he passed some years ago. But Thian took the reins and now came up with a second edition of it. So if you want to know all about the cryosphere, grab Thian's book. I believe Thian said people can get it at a cut rate. I believe you have that capability. But it is really my pleasure today to introduce Thian Gan, and he'll tell us all about the impacts of permafrost and warming in Alaska and Western Canadian Arctic. So you have the podium. Please take it away. Share your screen.
Thank you, Mark. I want to take the opportunity to thank Mark and the staff at NSD for their hospitality during my visit the last 4 months. And I'm wrapping my visit soon. We really enjoyed the visit, and we have managed to do an interesting project on climate change impact of permafrost in Alaska and Western Arctic of Canada. So I will first give you a few slides to give you an overview about permafrost, and then I'll go on to the project itself. So here shows you a picture of the Northern Hemisphere, the distribution of continuous, discontinuous, and sporadic permafrost. Okay, and the purple colors are permanently frozen ground. Blue is season frozen ground, and intermittent frozen ground are colored in orange. So what is permafrost? It's a frozen ground in which there could be a couple of answers. This is the kind of fun question I give to my students when I discuss the topic of permafrost. And usually they don't seem to be able to get the right answer. The right answer is the definition of permafrost is temperature remains below 0 degrees Celsius for 2 or more years. That is the accepted definition of permafrost, or frozen ground. Okay. Here shows you the distributions of permafrost of Northern Hemisphere and CALM site. CALM stands for Circumpolar Active Layer Monitoring Sites, where they monitor permafrost, how it changes over time for quite a few years using some kind of tubes and ground temperature interpolation techniques. To give you an idea how permafrost is related to the mean average annual temperature, here shows you the distribution of continuous, discontinuous permafrost and how it is related to the mean annual air temperature. And you can see that if the mean annual air temperature is less than -5 degrees Celsius or lower, you tend to have continuous permafrost. Otherwise, you may have discontinuous or sporadic permafrost. And so the definition of permafrost is the mean annual air temperature is less than -1 degree Celsius, then you can have what is called the discontinuous permafrost. If it's less than -7 degrees Celsius, you tend to have continuous permafrost. And season frozen ground are ground that is frozen for 2 or more weeks. And based on that definitions, you have about 24% of the Northern Hemisphere occupied by continuous permafrost, and about 50% of exposed land on Northern Hemisphere are discontinuous permafrost. Okay, in terms of area, permafrost lies about 22 million kilometers square exposed northern hemisphere land area. Maximum extent is between 60 degrees and 68 degrees north. Its thickness could exceed 600 meters along the Arctic coast of northeastern Siberia and Alaska. And so continuous permafrost means to say that greater than 90% of the area is frozen, and discontinuous is between 50 to 90%. Sporadic permafrost area where the percent of frozen ground is 10 to 50%. Isolated is if it's less than 10%. And the southern limit of continuous and discontinuous permafrost is approximately based on the mean annual air temperature of about -8 degrees Celsius and -1 degree Celsius respectively. Area of these three permafrost zones are about between 9.4, 6.7, 9.4 million kilometers respectively. And so the area of seasonal frozen ground is largest, it's about 55 million kilometers square, about 80% of the northern hemisphere's land area. Okay. Now, permafrost can be widespread if it's on high ground. So at about 20 degrees north, you can find permafrost, widespread permafrost, if the elevation is 4,500 meters or higher. But as you go further north, the altitude decreases to, let's say, about 1,000 meters at latitude of about 60 degrees north. Okay, you can map frozen ground using remotely sensed data, using sensors such as SAR, synthetic aperture radar, or passive microwave, which are of relatively low resolution sensors. And just a few definitions about the thermal relationship of permafrost. So thermal offset refers to mean annual ground temperature that is generally greater than the temperature on top of permafrost by about 0.1 to 1.2 degrees Celsius. Zero curtain means to say that during freezing, because of the release of latent heat of fusion to the atmosphere, initial ground temperature tend to be about 0 degrees Celsius. That's why it's called zero curtain. And permafrost is dependent on the freezing degree day or thawing degree day, which is usually the most popular method to estimate whether a place has a permanent permafrost or discontinuous permafrost and so on. So I'll show you a few equations here, give an idea what I'm talking about. Frost number, surface frost number is based on equation 5.1 there, which is square root of freezing degree day divided by square root of freezing degree day plus thawing degree day. And there's another definition based on equation 5.6 of Nelson and Carlton, but the first equation is usually a more popular equation to be used to determine whether a place has what type of permafrost. So to give you an examples, here shows you the mean monthly temperature of Inuit in Northwest Territory of Canada. And based on the frost number equation shown there, the frost number of Inuit is 0.647, means to say that Inuit has discontinuous permafrost, because to have continuous permafrost, your frost number should be greater than 0.67. And for Inuit is between 0.67 and 0.6, so it has discontinuous permafrost. Now, the thickness of permafrost varies. It could reach 1 kilometer or as deep as 1.5 kilometer, but that would take like at least 100,000 years for permafrost to be of that thickness. Okay? So the thickness permafrost is developed based on a balance between surface heat loss in the atmosphere and the geothermal heat flux from within the Earth. Yeah. And the temperature gradient is as number shown there. So from now on, I'm going to say a bit about the active layer, the layer above the permafrost that is frozen in winter and thawed in summer, or a seasonally frozen ground above permafrost tailor. So the next few slides, I'll show some examples taken from this book that I co-authored with Roger Berry, was published in 2022. So here shows you the seasonally frozen ground that is frozen in the winter but thawed in the summer. And the thickness of this layer is called the active layer thickness. And active layer thickness can vary from, let's say, 0.1 meter to close to about 1 meter, depending on the location and depending on the soil moisture and depending on the temperature regime. Active layer thickness, of course, tends to decrease with increasing latitude due to the lack of shorter thawing seasons, and a decrease with a thick vegetation cover or snowpack. Okay. Active layer thickness also depends on soil moisture that determine the soil heat capacity and its rate of temperature change due to heating and cooling. And it could range from as small as 2 centimeters at Mount Fleming in Antarctica to about 45 centimeters in Ellesmere Island of high Arctic in Canada to close to 1 meter at calm site. That is the circumpolar active layer monitoring sites somewhere in Northern Europe, to a few meters somewhere in Switzerland. And you can estimate active layer thickness using, for example, these Stefan's equations, which is the ground temperature during thawing seasons multiplied by the thermal conductivity of unfrozen soil and the latent heat of fusions and the time of the thawing seasons. So for example, if the average temperature is 5 degrees Celsius, thermal conductivity is about 1.6 joule per second meter degrees Kelvin, and if the time of thawing season is about 6 months, using Stefan's equations, the active layer thickness at the end of the thawing season, it should be about 0.87 meters over a thawing season of 6 months. And you can also estimate the rate of thawing front, how fast does the active layer increases in depth. Okay, using these equations, the rate of descent of a thawing front, dzt over dt, okay, using the same parameters as I did in the last example, the rate of thawing front is descending about 0.142 meter per month, or about 0.85 meter over a period of 6 months. Okay. Now, I will now show you a few slides about how permafrost looks like. So this is one picture of how permafrost look like. And because it's frozen, carbon is locked inside the permafrost. But once it starts to thaw, soil carbon could be released as CO2. But even though it's released, not all go to the atmosphere. Some can wash into the Arctic oceans. Here shows you an exposed ground of massive ground ice and somewhere in Russia. Yeah, QT, I don't know where that is. Okay. And you can see that the frozen ground, it's quite obvious. And I will show you just a few more slides about geomorphological features associated with permafrost. This looks like a little hill or a little mountain. It's called Pingo. Inside are mostly ice, massive ice that is produced through injections of water as the free thaw cycle goes on for years or for decades. Okay, it's an Inuit term. These features are found in the Mackenzie Delta area. And then you have what is called pausa. Pausa is a Finnish term. It means to say peat bog hummock with an ice core. And it could range in size from 1 to 8 meter high, 5 to 25 meter in diameter. Okay, so these are the features that are found in northern Finland. And you can have a thermocrust. It's a formation of hollows when ground ice, permafrost regions start to melt, causing the ground to subside or slump, and it can vary in size from 100 meters to as big as 15 kilometers in size, a depth of 3 to 40 meters. And you can find all this sort of thermocrust somewhere in Russia or in northern part of Europe. Okay, I will now start to explain the project that I've done with Mark for the last few months. We try to model the active layer thickness of a site in Alaska and the Western Arctic of Canada, shown in this picture here, using satellite data, airborne data from P and L band sensors, 51 sites on this permafrost dynamic observation project, Alaska and Arctic of Canada, that was conducted in 2017. Okay, here shows you some of these swaths, how do they look like. And this is called the above data set, this Arctic Boreal experiment. Okay, using airborne L and P band synthetic aperture radar to estimate the active layer thickness of 51 sites, 39 sites in Alaska and 12 sites in Northwest Territory of Canada. Okay, this data set consists of active layer thickness, vertical soil moisture profile, and its uncertainty of active layer thickness at about 30-meter resolutions. So I will now show you some of the data I've analyzed. The uncertainty of active layer thickness measured using this L band and P band synthetic aperture radar doesn't seem to be associated with the active layer thickness itself. You can see that the relationship is very small. R squared is only about 0.1. Okay, so uncertainty based on this sort of estimate active layer thickness using L band and P band SAR sensors varies, and it is not dependent on the active layer thickness itself. And we try to relate active layer thickness with this modified Stefan's equations. K is a conversion factor into square root of total of thawing degree day for the thawing seasons, and we get very good results based on the first equations. The R squared is 0.978. The second equation is to associate active layer thickness with K into square root of thawing degree day divided by the soil moisture, and still we get very good relationship. So we can see that active layer thickness is driven predominantly by the thawing degree day, and even though it's also related to other factors such as the soil moisture and also the vegetation cover and few other factors. Now, active layer thickness is expected to become thicker because of global warming impact. Here to show you just a slide taken from the IPCC report. IPCC report has been warning that the global warming is attributed to the human impact, and it become more and more assertive in pointing human activities are the main cause of climate change that have been observed in the last couple of decades. Especially in the last report, AR6 report, it says that it is indisputable that human activities are causing climate change, making extreme climate events more frequent and severe. And also, because of warming, we expect active layer thickness to also increase. So now I'm going to show you some results based on what we have studied over how active layer thickness changes under the effect of global warming. Now, first of all, I'm going to show you just two pictures about the global warming on a global scale for the last 70 years or so. Is about 1.2 degrees Celsius throughout the Earth. But if you look at the global warming impact in the Arctic, latitude between 65 to 90 degrees north, for the same period, Arctic has been warming much more compared to the global average. It's about 4 degrees Celsius. And this is based on some reanalysis data of NASA. Annual composite anomaly between the two periods of 1950 to 2022, using 1991 to 2020 as a climate normal, you can see that some part of the Arctic has been warming about 3.5 degrees Celsius, much higher than the global average, especially near the Siberian area. Okay. In the winter months, especially December to February, from 1950 to 2022, some part of the Arctic has warmed as much as about 6.5 degrees Celsius. And this phenomenon that Arctic is warming much faster than the global average is called the Arctic amplifications. And if you look at the Arctic sea ice extent for the last 40 years, you can see that Arctic sea ice has been declining very significantly, okay, over the last 40 years because of the warming going on in the Arctic. Okay? And the sea surface temperature seems to have gone up to as high as like over 10 degrees Celsius over the same period. So I did a study to look at how the active layer thickness in the study sites, 51 sites in Alaska and Western Arctic of Canada, how would that be impacted by global warming using the SSP scenarios of the CMIP6 of 7 CMIP6 GCM. So SSP stands for Shared Social Economic Pathway, and using 3 scenarios, the most modest scenario is SSP 1.2.6, SSP 4.5, and the most severe projection SSP 8.5. And of course, we would like to limit ourselves to SSP 2.6 so that if we can achieve a warming of no more than 1.5 degrees Celsius by the mid-2050s, that is what is the goal of the COP27 meeting recently in Egypt. Okay, so look at those SSP. Based on those SSP scenarios that have been downscaled based on 7 GCM, active layer thickness is projected to increase from about 0.5 meters. Okay, this is the observed active layer thickness for this 51 site. And if we were to estimate the impact of global warming using the thawing degree day, the modified Stefan's equations, active layer is projected to increase, especially under SSP 8.5 scenario in the 2080s. Okay? And it depends on which GCM's projection that you are using to estimate the change in active layer thickness. This is based on the MPI GCM, and then this is based on the UK GCM. This is based on a few other GCM, but you can see that active layer thickness is projected to increase fairly significantly, especially under the most severe projections of SSP 8.5 in the 2080s. Here shows you a few more other projections, but you can also see that the projected change in active layer thickness also vary depending on which GCM that you are using. Okay? And so there is quite a wide range, and so there's quite a bit of uncertainties. And active layer thickness, how is it going to change? We can project, but we know that there's a lot of uncertainties but this is to summarize the projected active layer thickness compared to the observed average layer thickness for this 51 sites, which is about 0.48 meters. Active layer thickness projected to increase to as much as about 0.7 meters under the projection of this UK GCM, UKESM1. Okay, the more modest projections in the 2050s, based on the SSP1 2.6 scenarios, active layer thickness is going to marginally increase from 0.48 to about 0.51 meters. So that is quite a range. If it's about 0.7 meters, that means to say that the active layer thickness of these 51 sites in Alaska and Western Arctic Canada could increase by about 45%, or it could increase much less than 10%. Okay. And associated active thickness is what is called the settlement. Okay, when the active layer thickness increases, the ground tends to settle. Okay, and that is based on these equations. Settlement is due to the change in active thickness multiplied by the volume of the ice in the soil layer. Okay, and settlement index could range depending again on the SSP scenarios. And I show you this is based on SSP scenario MPI GCM, which is a more modest projections compared to the SSP scenario for UKESM1, which is the most severe projections. And the settlement index could range from less than 1 centimeters to about close to 0.3 meters or 30 centimeters. Okay. And how will this impact the Arctic infrastructures? As you would expect that with thicker active layer thickness, there will be more sediment, and Arctic infrastructure, which is built on the foundation of permafrost, could be very seriously affected. Okay. So here shows you the range of sediment index, and that could range from close to 7 centimeters to about 1 centimeters. Okay, depending on which GCM's projection that you're using, and depending on which SSP scenarios, and whether it's 2050s or 2080s. Okay? But you can see one thing here. The coefficient of variations, that is the sediment index, how it varies across these different sites is quite high. Often it's more than 1. Means to say that the standard deviations of this sediment index is more than the average value of the sediment index. Means to say that there's a lot of spatial variability, and that means to say that there's a lot of uneven sediment. And because of uneven sediment, Arctic infrastructures is more likely to crumble. I'll just move on to show you a few slides about the temperature of permafrost. Okay, this is based on a study, look at different permafrost sites across northern Alaska, northern Canada, and Siberia. And you can see that in different sites, you tend to have higher annual permafrost temperature over the year since the 1980s to close to 2016. And some site temperatures will increase by as much as about 2 degrees Celsius. Some site, they do seems to have much changes in the permafrost temperature. And of course, if there's more increase in permafrost temperature, there's going to be more thawing and thicker active layer thickness. Here shows you another study in different parts of Europe, and you can see that active layer thickness in some places has increased by 1 to 2 degrees Celsius. Some places they don't seem to have much change. So it depends. It's a lot of spatial variability. Now, we expect Arctic to be warming much faster than the rest of the world. Some project as much as 7 to 8 degrees Celsius, but there's a lot of uncertainties, and especially the reduction in the permafrost extent, the projection could vary quite a bit, but because frozen ground takes time to thaw, the predicted reduction permafrost extent by 2100 is only about 20-24%, even though temperature can increase by 2.8 to 7 degrees Celsius. Okay, but we know that the extent of ice-rich permafrost degrees in response to warming in the next 100 years remain to be very, very uncertain because of many uncertainties, many unknowns that we are still trying to figure out. And if permafrost thaw, you can see the erosion of some coastal area in Alaska, and when the permafrost, the carbon that is frozen in the permafrost is going to reach the atmosphere, causing more warming, which is a positive feedback. So I will show you the last few slides on the thawing of permafrost impact in the Arctic infrastructures. Here shows you on the left figure a Russian apartment building. The corner collapsed from uneven permafrost in somewhere located in Chersky, and this is based on a picture taken by Dr. Romanovsky of University of Alaska Fairbanks. Okay. And the picture on the right shows you the building perched on uneven thawing of permafrost are cracking and buckling. Okay. And besides infrastructure impacted by uneven thawing of permafrost, you could get into some very major environmental pollution problem. So here shows you a picture of an Arctic site suffer major oil pollution after a fuel tank in Russia collapsed. Okay, again because of uneven thawing of permafrost, and spilled about 20,000 tons of diesel in the environment. This happened in not that long ago, in May 2020, and it could take over 10 years for the Arctic ecosystem to recover from this massive oil spill because of the collapse of a fuel tank in Russia. So Arctic infrastructures play a very major role in the well-being, health, socio-economic development of the Arctic communities. Okay, based on a study, about 35 to 200 rural Alaska communities could face serious threat from thawing permafrost. Damage to the public infrastructures in Alaska could cost $5.5 billion by late 21st centuries. Okay. So about 1/3 of pan-Arctic infrastructure could be affected. 45% of the hydrocarbon extraction fuel Russia in the Arctic region could be affected by thawing permafrost. It could cause serious damage to the building environment in the 2050s. For example, certain railways in Qinghai, Tibet, Eastern Siberia, and then some pipelines in the Pacific Oceans and Yama natural gas pipeline. These pipelines under the thawing of permafrost could crumble and could cause very serious spill problems. Okay, so in summary, the above data set, which was acquired using airborne L and P band synthetic actuator sensors to estimate activity thickness for 51 sites of Alaska and the Arctic. And we also model the activity thickness using the modified Stefan's equation shown there, where thawing degree day is taken from air temperature for ERA5. And based on the SSP scenarios of 7 GCM, we project the activity thickness of these 51 sites in Alaska and the Western Arctic of Canada is going to increase somewhere between 15 to 45% by 2080s, and the projected sediment could increase to almost 7 centimeters, which will impact the Arctic infrastructures, especially due to the different sediments because of the high spatial variability of active layer thickness and the volume of ice. So this is basically my presentations and today's talk, and I'll be happy to answer any question you have regarding my presentations. So I'll stop sharing.
This was just wonderful, Thian. I think, we learned a lot about permafrost and what is happening. There's a lot going on up in the Arctic. So we can open it up for questions here. And I think if you just put them in the chat, it's probably going to be a better because we have quite a few participants. And Ms. Stia, I will ask you to read off the questions as they come in, because as you can see, I'm in the middle of having a haircut at the same time. Strange how we get double booked sometimes, but in this case, it was having a haircut. So please, questions from anyone at this point. So this was great,
I also let people unmute themselves.
Oh, here comes the first one. So yeah, you can take it away, Ms. Dia, please.
Sure. So Florence wrote, thanks for the detailed overview. Those interested in permafrost, note that how permanent is permafrost? And I think, Florence, were you talking about a classroom activity? And then students are, it doesn't look like a question. It just looks like
no, Ms. Tia, it's not a question. I just was advertising the fact that we have this classroom activity that links to a permafrost data set, and it does for students essentially what your speaker did at a much higher level, and that's compare permafrost ground temperatures with some excuse me, air temperature data sets. Walks people through how to do that. And there was a special permafrost data set developed for that by Thian Yew Gan and Oliver Fraunfeld. So if you're interested in that, just see the chat for the links.
So let me just try to answer the first question. How permanent is permafrost? I would say that unless the temperature drops drastically, permafrost is going to be there for a long, long time. And permafrost could increase in its area extents because of global warming impact. And active layer thickness will become thicker and thicker because of global warming impact, as what I've shown in this study using the SSP scenarios of the CMIP6.
I have a question, if you can hear me. So in terms of the permafrost carbon feedback, how significant do you think this could be? There are very, very different estimates of how much carbon could be released to the atmosphere, primarily as carbon dioxide, but also as methane, but they're very uncertain. So what's your view on how strong that feedback could be?
I think there's so much uncertainty. I can't give you a definite answer, but I believe there is going to be some positive feedback because when carbon is released under thawing permafrost, you're going to get more CO2, which cause more warming and which cause more thawing of permafrost. So it's a positive feedback process. But there's a lot of uncertainty because of the fact that we do not know what is buried underground. And also, it takes time for permafrost to thaw because it takes time for the heat to go down to the thawing layer because even though air temperature could be much higher, but the ground response time in thawing is going to be quite slow. But again, this is something we don't quite know yet. But we can roughly estimate the active layer thickness is related to the square root of the thawing degree day based on monthly air temperature. And in this study that we had just done, we used the ERA5 soil temperature, and we can relate the active layer thickness based on the soil temperature as well as the air temperature. So they are related, and I think, to make the answer short, I believe that there's a positive feedback, but as to how fast is the feedback, I don't really know. I can't answer the questions.
Looks like there's another question coming in on chat.
Yeah, Lawrence said, very nice talk. Professor Gan, do you think that possibly including soil ice content, not just temperature state, in describing permafrost soil properties may provide more useful insight, especially for predicting thaw impacts?
I think so. In fact, I show you one of the slides, the scatter plot of the active layer thickness versus the one that is estimated using the modified Stefan's equation. In one of the two scatter plots, I include the thawing degree day and also the soil moisture. But the result seems to be comparable. So soil moisture plays a part in the thawing of the permafrost, but I would say that the thawing degree day seems to play a more important part compared to the soil moisture. Because the soil moisture, based on what I've seen, looking at all those data that I've analyzed for the last few months, they ranges between about 0.3 to about 0.6 or 0.7. It doesn't seem to change very much. And so, the thawing degree day could vary a lot depending on, especially when you talk about climate change impact, it depends on what scenarios you're using.
I have one more question for you, Thian. So what about subsea permafrost? You know, there's been talk about massive methane releases from the seafloor through the thawing of subsea permafrost, and that's fossil methane. You know, it's not recent stuff. Some people say that, oh, it's a ticking time bomb. Other people have said, well, no, you could really not have a quick massive release or anything like that. You know, have you looked at that much? What's your view on that?
I haven't looked at that myself, but I know that methane is a much more powerful greenhouse gas compared to CO2. In terms of what's called the global warming potential, by definition, CO2 has a global warming potential of 1. Methane has an average global warming potential of about 25. So methane is a much more powerful greenhouse gas compared to CO2, but the quantity of methane is much less compared to CO2. So the overall impact, I would say, is more of CO2's warming effect compared to methane. But as to what you say about the release of methane from the ground, that could have some local impact. I would say that in regions located in places where there's a massive release of methane, again, I do not know where it happens, whether it has happened or not, there could be much more faster thawing of permafrost because of the because methane is a much more powerful greenhouse gas compared to CO2. But on a global scale, the impact comes mainly from CO2. But in local scale, it could be methane, which the impact could be much more compared to CO2.
Looks like another question's come in on chat. All right, I'll get it. So, will the thawing of permafrost? This comes from Dabby to everyone. Will the thawing of permafrost vary at all between continents like North America and Northern Europe, Asia, or can we predict that it will be similar? In other words, will it be varying across the landscape, or will it be similar to other areas? And we have someone else with a hand up.
I believe it could vary quite a bit. It depends on the degree of warming. Permafrost thawing depends on the increase in air temperature and also the ground temperature. And I show you one of the slides where warming is much more in some part of the Arctic than other parts, especially one of the slides I show you somewhere in Siberia, the warming could be in the past 70 years, like about 3.5 degrees Celsius. Some part is much less.
Double booked by mistake. Well, I couldn't change it.
Yeah, so I believe it's going to vary quite a bit from locations. Also depends on the kind of soil you have, the thermal conductivity of soil, and the soil moisture, and the structure of the soil strata, and also the impact of vegetation cover and snow cover. All of this is going to finally give you the degree of thawing. And I believe the spatial really is quite high.
And it looks like Paloma has a hand up.
Yes, I'll ask directly if you don't mind. Otherwise, I can also write it down. My question was following. First, thanks very much for the great talk. My question is, you were showing how to compute that you computed the settlement index, and I'm wondering about the ice volume values that you used. So, are those measured at the individually at the above sites, or do they come from those ice volume values? Do they come from another large-scale source? I'm wondering because ice volume is not an output of the above SAR estimates, right?
Yeah, it gives the soil moisture, and assuming it is frozen, that soil moisture provide you the more or less the ice volume, and then also you can use the ERA5 data. They do provide some of those information as well. So there are a few sources there you can use to estimate those. The one I show you is based on this the above data set that I use.
Oh, okay, right. Thank you very much.
Thank you.
But this has been great, and it was just a great talk because I was really at a nice level here, you know, where everyone could understand what was going on and the importance of permafrost across the northern landscape and how it's changing and what the impacts of it will be. So Thian and I will continue to work together on some of this work, and you'll be heading back to Alberta fairly soon, as I understand it. But he's still around NSIDC, so if you want to come by and chat, I'm sure Thian will be around to help with your questions.